In this video, we're going to be going over semi-log plots, section 2.15 for AP Precalculus. Specifically, we're going to be using the Desmos online free calculator. If you like to use a TI graphing calculator, you shouldn't watch this video. Go look elsewhere for those videos that talk you through and follow and guide you how to use your TI graphing calculator for using semi-log plots. Here for this one, we're just going to be using the free online Desmos calculator. So, Sully wants to open his own butcher shop, the New York Metzgerei, where he can sell his signature product, salami picante. Now he has to cook the meat and then let it cool while recording the temperature during the process. Now one day he observes the following temperatures. So we have all these temperatures. As time goes on, the temperature gets closer and closer to room temperature. And so this represents not the absolute temperature, but how many degrees above room temperature it is. So the longer it goes, the closer and closer it gets to room temperature. So if I want to graph this over here, we have 0 degrees, 10 degrees, then we have 20 degrees, 30 degrees, 40 degrees, and 50 degrees. That's our measurements for temperature. Now, so at 10 minutes, it's at 51 degrees. At 14 minutes, it's at 41 degrees. At 20 minutes, it's 30 degrees. At 22 minutes, it's at 26. At 30 minutes, it's down to 17. At 36, it's at 11. At 40 minutes, it's at 8. 42 minutes, it's at 6. And 44 minutes is 5. And if you notice, we've got a kind of a curve going on here. This is consistent with an exponential function because the temperature is going to get closer and closer to 0. It's going to get closer and closer to room temperature. So this models an exponential function. So because this is exponential, what we're going to do is we're going to give this to Desmos. So I've already plugged this in. So if I plot these points, there we go. Now I want this to show an exponential regression. So right now it's linear and it doesn't quite fit the points, but if I make it exponential, you see my r squared is almost perfectly 1, meaning it's almost a perfect fit for an exponential model. So that regression equation is y equals 93.92735 times 0.942482 raised to the x power. Now, then it says take the log and rewrite the equation. Okay. So what that means is we're going to take log of this equation. So log of y is equal to log of this whole expression, 93.92735 times 0.942482 to the x. Now, using our properties of logarithms, what we can do is we can break this up because we are multiplying these two quantities. So that equals log of 93.92735 plus log of 0.942482 to the x. Now we can also use another log property where we have an exponent that we can bring down in front. And I can write this as log of 93.92735 plus x times log of 0.942482. And using my calculator, we can write what these values are. So log of 93.92735 and log of 0.942482. So this equals 1.97279 minus 0.0257x. So the kind of function that we have now is a linear function. And that's what we're talking about, is we want to do what's called straightening the data. And so what we're saying is, look at this graph. Notice that it's unlike the other grids that you've seen before, because now the y values are not equally spaced out like they are for x. Notice that we go from 1 to 10 and then 10 to 100, and those are the same widths. So we're going by orders of magnitude here. So if I plot this now on this scale, we have 10, 51. So here's 10, and then we have 20, 30, 40, 50. So that's right about there. Then we have 14, 41. So that's going to be about there at 20, 30. 22, 26. 26, 21. 30, 17. 36, 11. So that's close to 10. 40, 8. So that's going to be just under. 42, 6, 44, 5, now if you notice, the points, they kind of line up a little bit. That tends to happen. And so what we just did, by taking the log, that demonstrates that. Now, we want to complete this table. Now, to make this easy, we're not going to use what they did, because that's using a TI graphing calculator. So how do I straighten the data? So what I'm going to do over here is, in Desmos, I'm going to type in log, parentheses, always got to have parentheses, y1. So there's our data. So 1.7, 1.6, 1.5, 1.4, 1.3, 1.2, 1.0, 0.9, 0.8, 0.7. I'm just rounding to the nearest tenth. So now what they're telling us is, what do we notice if we plot this data point? Okay. Notice, see how the dots, they almost perfectly line up. So they form a linear function. Now, they want us to run a linear regression of this. Now, when you have multiple columns now you have to tell Desmos, we're using the same x values, but now which y value? We want to use log of y1. So I want to change this to a linear regression, and I want to change this to log of y1. And if you notice, what we got was pretty close to what we came up with by hand. So log of y equals negative 0.0291x plus 2.045. And we always leave it as log of y to indicate that we've took the log of this. So with this example, we'll do the same thing. So I'm going to cross this out. So here's my data. So let's take a look. So here's how our data looks. So if I want to scale this, for x, I'm going to go by 2s. 2, 4, 6, 8, 10. For the y's, I'm going to go by 200s. 200, 400, 600, 800, 1,000. So I have 2, 10, 3, 21. Now at this scale, 10 and 20 are almost indistinguishable. At 5, whoops, that should be at 3, shouldn't it? Yep. Then at 5, we have 93.9. That's practically 100. Then at 7, we have 400. So just above 400. And then at 8, we have 869. So that's almost 900. So that's what that looks like on the linear scale. But what about on log scale? Now you can actually do this in Desmos. If I click Graph Settings and go to More Options, I can make the y-axis logarithmic and make it go by. And so now we go by powers of 10. So I have 10 to the first, 10 to the second, 10 to the third. But notice that the x's are still preserved. So 0, 2, 4, 6, 8, and 10. So at 2, we're at 10. At 3, we're at 21.3. At 5, we're at 93. So that's just about 100. At 7, we're at 400. So 2, 3, 4. And then at 8, we're at 900. So this is how you can get Desmos to show this on a semi-log plot. Now, to compute the log values, we'll type in log parentheses y2. And those are our values. 1.0, 1.3, 2.0, 2.6, and 2.9. So now we want to find a linear regression for this line of the log data. So when I click on the regression, I need to make a linear regression for log 2. So log of y equals 0.3224355x plus 0.36024. Now what I forgot to do above was to find linear regression for the untransformed data. That is this data right here. So let's do that. This was exponential. Now notice it's showing an exponential even though it looks like a line. And that's because if I turn my y-axis back to linear, now it looks like a curve. But when it's in logarithmic form, an exponential looks like a straight line. So this actually is y equals 2.3 times 2.0999 raised to the x power. All right, so hope this helps, and hopefully you can use Desmos to find these regressions.